So another application in the physics context to integrations is finding the pressure on a vertical wall. Okay, and here I highlight the vertical wall. Okay, not the bottom of a. So for example, a dam. Okay, a dam is a vertical wall. The bottom of a sort of dam is this reservoir, so it's just the ground. But we want to know the pressure that is applied on the actual wall itself. In general, if you know you're standing and there is this much fluid a distance d above you, the pressure that you'll feel is this right here. Okay, you'll use delta is equal to rho g sometimes, where rho is the density, g is the acceleration due to gravity, the 9.8 meters per second squared, and d is the depth. This also works, for example, in water, so any fluid. And so the force that you get, the formula for the force on a dam or any vertical wall for that matter, is going to be rho g a minus y, okay, where a is the height of the fluid level, and wy is the width of the wall, okay, area. This wy dy is the area of a strip on the vertical wall. So you'll take the pressure and multiply it by the area of a strip on that vertical wall to get the total force, because pressure is force over area, and so the total force is pressure times area, and that's what you're doing over here. And you're looking at, an object that is, or a point on the wall that's a distance a minus y, so at a height y, okay? And so above it, there's a minus y fluid. So that's the depth, is a minus y. The base of the dam is 0, and so you integrate from 0 to a, the height of the fluid. And here I emphasize it's for a vertical wall, not the bottom of the volume. For the bottom of the volume, you just take rho and multiply it by the volume of your object. Assuming rho is constant, you just take rho and multiply it by the volume of the fluid, and that will give you the total mass multiplied by g, and that's the weight. And so the bottom applies a force equal and opposite to the weight to keep that fluid from falling. Okay, and so this becomes clearer once we look at a concrete example. So here we have the problem: a large vertical wall dam in the shape of a symmetric trapezoid, so this right here, has a height of 30 meters, a width of 20 meters at its base, and a width of 40 meters at the top. Okay? What is the total force on the face of the dam when the reservoir is full? So it's all the way full. Okay, we're going to choose a coordinate axis here, and we're going to put the base of the dam at y equals 0. Okay? And we're going to place this symmetric about. So the face of the dam is going to be symmetric about the y-axis. Okay, that just makes computing the width easier. So we're going to find the width function. And notice here we have two different functions. For one of these is y is equal to positive, so it has a positive slope. The other one has a negative slope. Okay. Another way of seeing that, okay, is to just, since we chose our coordinate axis to be symmetric about the y-axis, then we just take that line there, and so we just connect these 2 points. So y minus 0 is equal to the slope is going to be the rise over the run. The run is going to be 20 minus 10, and so there's your 10 there. Your rise is 30, your run is 10, and x minus 10 is going to be this value here. That's a 10 there. Okay? That is a 10 over there. And so we have the slope in a general point 10, 0 that we use to get x as a function of y. And again, because we chose this to be symmetric so we chose our coordinate axis to be symmetric, we just multiply by 2. to get the total width. And here goes your total width. Okay? And now we carry out the integration from 0 to the height of the fluid. The height of the fluid is going to be 30. Y equals 30. Okay? And this A minus Y is indeed consistent with integrating to 30, because, you know, if this is some arbitrary Y, well, then this is 30 minus Y. And so you could see where this 30 minus Y is coming from. That's the depth that you're at, right? And so the pressure at that point is going to be, based on this formula here, rho times G times 30 minus Y. That's the pressure felt all along that depth there, okay? And the pressure is the same in all directions. So once you're at a particular depth, the pressure is going to be the same on the force of the wall, right behind the wall, you know, anywhere around that depth is going to experience the same amount of pressure, and it's going to apply that pressure on the vertical wall. This is a vertical wall. And so if you know, we're going to take a small slice of that, and so here's your dy at y, okay? And so we'll take the pressure at that depth and multiply it by this dy. So we're going to get a small area, you know, that depth with that small area, that's that small area here, okay? That's wy dy. And so having set up the formula now, which is the hard part, the rest is sort of carrying out the integral, and you get, you just find the antiderivative, plug in the bounds, and you get that value there. And you just learned how to compute the total force on the wall of a dam.